Everybody. Today we're going to be talking about potential difference and how that relates to electricity and the effects that that difference in potential from positive to negative and what effect it can have on charges. So I have set up a parallel plate system here. So I have a plate of positive charge and a plate of negative charge. That's similar to what we created using our fly sticks in class. And you can see that there's a consistent electric field in between them, and those field lines are parallel, except when you get to the outside edges of those plates, then you get those edge effects where the electric field lines are a little bit curved, but still going from positive towards negative. And if I take this positive test charge here, and I put it inside my electric field, this little guy is going to be feeling a force. Because it's positive, it's going to be repelled from the positive plate and being attracted to the negative plate. So it is going to want to naturally move to the right. And because that is a force, F equals ma, it is going to be accelerating to the right and speeding up, gaining some velocity the whole time it's inside that field. All right, but what if I don't want that charge to move to the right? I want to move it to the left. And in order for me to do that, that is going to require some work from me. I'm going to have to expend some energy to get that point charge to move to the left. Then naturally it would want to move back to the right. And because if something is moving, it has energy. And because it's gaining speed, because F equals ma, then it is gaining some kinetic energy. And so work is being done on that point charge, whether that is me moving this thing against the gradient in the opposite direction that it wants to go, or it's being moved by that positive charge towards that negative charge in the natural way that it wants to move. Either way, there is going to be some energy change. And anytime there's an energy change, especially kinetic energy change, we call that work being done. And so that amount of work that is done is the measure of the potential difference. So potential difference, written as V, and it's written as V because the common name for this is voltage, but don't think about it as voltage. We're going to think about it as potential difference. Volts are the units associated with this. But we need to remember that what causes a voltage or a potential difference is a difference in charge. And the greater that difference in charge is, the more volts your system will have. So the potential difference between 2 points is the amount of work that is done. So we have some work being done, and that work is being done per unit charge to move a point charge from one point to another in an electric field. So if we're moving our electron or our proton from one point to another inside an electric field, how much work did that take? Or how much work did my electron gain? How much energy did that electron gain? That is what our potential difference is. So the equation that you'll see in your data booklet, V is equal to the work done per charge, per unit charge, so for a whole coulomb. And we know that work is a type of energy, so we've got joules per coulomb. And the common name for that is volts. And so the more volts you have, you can see right here I have a 9-volt battery. What does that 9-volt battery mean? That means that if I take this and attach this thing to a wire, and inside that wire I've got a whole bunch of these little electrons that are free to move around. For 1 coulomb of charge that I move, I'm going to use 9 joules of energy. So if I have a potential difference of 9, and I'm moving 1 coulomb, how much work was done? 9 joules of work. And so let's say that just for argument's sake, this side over here is positive, this side is negative, and I know that these electrons are going to want to move right to left. And so if I look at this one on the right and say, okay, it's going to go that way. How much energy is that thing going to gain? Well, it's going to gain 9 joules of energy per unit of charge, per coulomb of charge, because this is a 9-volt battery. If I had just a AA battery, that's a 1.5 volts. That same electron moving through that same wire, going from one side to the other, would only gain 1.5 joules of energy. Or that battery would only be using 1.5 joules of energy to make that electron move. And vice versa, if I said, okay, inside this electric field, because there would be an electric field here, from positive to negative, so I'm going to draw like my electric field inside my wire, and that electric field is what's making these electrons move, and I grab this one, and I'm going to move it against the grain. It wants to move down towards the positive, but I'm forcing it to go the other way. I would have to expend 9 joules of energy to move a coulomb of electrons, or a coulomb of charge, through that wire against that pattern, against that potential difference. So in our outlets, we have 220 volts, so 220 joules per coulomb. In the US, it's 110 volts, so 110 joules per coulomb. And that is the definition of potential difference. There is one thing else that I want to talk about. I'm just going to go for this. It wasn't quite planned, but we know that work is being done on our charge that we're moving around in our system. Actually, there's 2 things I want to talk about. Before I start talking about that work, let's say, okay, I have this charge right here, and I want to move it towards my positive plate. That means I have to give it some energy. So I'm losing energy. This positive charge is going to gain some energy in order increase potential energy so it can go back towards the negative side and turn that potential into some kinetic energy. But what happens if I move this perpendicular to those field lines? Am I doing any work? So for me to move this guy across my electric field, not getting closer or farther from my parallel plates, and that actually would mean that I'm not doing work. I'm not changing the potential energy of my charge, because it is the same distance from that positive plate. It's not being repelled anymore or attracted anymore to that negative plate. So by moving this thing perpendicular to that path, or perpendicular to those field lines, I am not changing the total amount of energy inside that that test charge has. So the only way I'm changing that is by changing the distance that this unit charge, or this test charge, has, or is in relationship to those parallel plates. So what if I move it like this and I'm following some really crooked path? Does it matter that I went all the way down here and then all the way up to the top and all the way down here and then all the way back to the middle? And that answer is not really. The only thing that matters is going to be this distance inside the field that I moved this. So if I said, okay, I've got one positive charge, I'm going straight across the shortest possible distance. Then I take another charge. Let's see if I can grab my charge again. And yeah, I thought I'd grab that piece as well. But now I'm moving it from here, down here, then up here, then down here, then up here, then down back. And I ended up in the exact same place. It would have the exact same amount of energy, because the path of this that I take with my charged particle doesn't matter. It only matters the distance that it has traveled in relationship to that positive plate and that negative plate. So work, that was point number 1, path doesn't matter that I take. Point number 2, I want to get one other equation that's not in your data booklet, and this might be helpful, but it's just a little trip down memory lane. Work is equal to force times distance, cos theta. So if I'm looking to say, okay, I know that this is a positive charge inside an electric field, it has a force acting on it. How much work came out of it? Well, it depends on the total distance it traveled inside that, and that force was acting on it. This cos theta, because these are going to be parallel to each other, that's going to go to 1 because that angle between the displacement and the force is going to be 0. So the work is equal to the force times the displacement of that object. And we just defined the voltage is the work done per unit charge, or per coulomb. So we have one equation, we have two equations. And now our third equation that we can see deals with this electric field. This electric field is the force per unit charge. And I'm going to put all these things together and then cancel some things out, and we're going to see what magic happens. I can see I can substitute equation 1 into equation 2. And my voltage is equal to the force times distance over unit charge. And I can easily write this in a different way. My potential difference is force per unit charge times distance. And yeah, that makes sense. But I see this term right here and say, okay, oh, that looks like equation number 3. So my potential difference is equal to the electric field times the distance. So if I know my potential difference, let's say my potential difference between these two plates is 100 volts, and they have some distance between them. That distance is 1 meter. I could determine what that electric field would be inside. But then I increase the distance of those parallel plates. That means that the electric field must decrease because my voltage is remaining the same. My potential difference is still 100 volts. So this is equation number 4. I will say that it might be useful for you, not given in your data booklet. It's not a hard derivation. You could probably figure that derivation out, but it's one thing that might be helpful as we solve some problems. All right, in summary, what is potential difference? Potential difference is the amount of work done per unit charge as I move a point charge through a electric field, whether I am going to be giving energy to that point charge, or that point charge is moving from an area of high potential while it's close to the positive charge to an area of low potential energy when that positive point charge comes close to that negative plate. And so what did that potential energy do? It turned into kinetic energy, and work was done. All right, I hope that was helpful. I know it wasn't super clear at some points, but we'll talk in class. I will see you guys then.